Let's start with the problem. Now, last time we talked about polar coordinates and integration in polar coordinates. And we're going to go into that sort of theme later on of saying, well, what does it mean to integrate in different coordinate systems? Why would we want to do it, and how do we go about doing the process? So polar coordinates is just an example. And the idea of polar coordinates is to say, maybe a problem can become simpler if we switch to a different coordinate system. So here's a problem. Find the integral from 0 to 1, integral 0 to x, arctangent y over x dy dx. Now, at first glance, this seems to have absolutely nothing to do with polar coordinates. I mean, among other things, you might say, okay, let's sketch our region. So what's true about x? 0 to 1. So I'm going from x equals 0 to x equals 1. And then y, well, y goes from y equals 0, which is the x-axis, up to y equals x. Which means our region is a triangle. Not very polar-like at all. Polar is very circle-friendly. So it's not immediately obvious that this is a problem that polar coordinates might be helpful to do. But this function, arctangent y over x, that's an unusual function. And it's not immediately obvious how do you work with this function. So let's think about what's true. Now, what do I have? Well, suppose I'm in the plane, and here's a point, I say x comma y, and I ask the question, what does arctangent of y over x correspond to? And this is, what we're trying to understand, because really now we're thinking about inputs are as a two-dimensional thing. It's a point in the plane. And I want to understand what is this expression I'm trying to integrate, what does it correspond to? Well, you can think about x and y as actually being measurements of something. So, for example, y is that distance there. And x is that distance there. Because x indicates how far you move in this direction that we call the x direction, y how far we move in the y direction. And now I say, oh, wait a second, if you were to make a triangle here, and we're taking the arctangent of y over x, that would fit into this corner. So I can think of arctangent y over x as being this angle here, which we call theta. Say, oh, so in polar coordinates, this unfriendly looking expression all of a sudden becomes super friendly. So that's why switching to polar could be a helpful thing to do. So let's try this. So we're going to our switch to polar. Now, there's a couple things we have to do. Really, every integral has three pieces. We've just focused on the function. So that becomes theta. How about dy dx? What will that become? R dr d theta. Because dy dx, that's like our bit of area, change in area. And in polar coordinates, that corresponds to r dr d theta. R dr d theta. Okay. Now we've got to talk about the angles. Well, look at our region. Which angle do we start at? Which angle is this positive z, probably positive x? 0. Which angle do I end at? Pi over 4. Yeah. It's following the line y equals x. Now I have to think about r. Well, we start from the center, which is the origin, and we go out until we hit this curve. So we start at 0, and then we go out till we hit x equals 1. Now there's a problem with x equals 1. It's x, that's Cartesian. We've got to switch to polar. So what can we do for x? R cosine. So r cosine theta equals 1. And remember, because this is an r bound, the dr, I have to solve for r. So instead of r cosine theta equals 1, we say r equals secant. So we're going from 0 to secant theta. Okay, so now we have a plan. We start the integral. So this becomes integral 0 to pi over 4. And we're integrating with respect to r. So it'll be 1/2 theta r squared from r equals 0 to r equals secant theta d theta. Now the nice thing is when you plug in 0, you get 0. And if we plug in secant theta, we're going to get 1/2 theta secant squared theta d theta. All right. Now, is it possible for us to integrate 1/2 theta times secant squared theta? I mean, hopefully, it is, after all, an important part of this problem. What tool do we need? Integration by parts. Now, I don't want to give you the idea that we're going to stress integration by parts. That's really a Calc 2 tool. It's a nice tool to know, and you really should know it if you're going to go through calculus. If you're not super comfortable, you don't have to be super comfortable. But it's nice to remember that, hey, we can do stuff. Doing stuff is good. So we have these two things, the secant squared theta and, say, the 1/2 theta. So integration by parts says you want to integrate one and differentiate the other. Well, which one should we integrate? Which one should we differentiate? Integrate secant squared because that has a nice integral. And we also differentiate theta because the differentiation of theta gives us 1, which is very nice. So that tells us that we'll think of this 1/2 theta as our u, secant squared as our dv. du will become 1/2 d theta, and then v will become tangent theta. So we get u times v, 1/2 theta tangent theta, and then you evaluate at the points, 0 to pi over 4, then minus the integral of v du. So 1/2 integral tangent theta d theta from 0 to pi over 4. Now, do we know the integral of tangent theta? For instance, is it on our list of 10 integrals that we should know? Yeah, it's on our list of 10 integrals we should know. What's the integral of tangent theta? I'll give you a hint. It starts with log. It's log secant. All right. And now we just, to finish, need to integrate from 0 to pi over, evaluate from 0 to pi over 4. So we get 1/2 times pi over 4 times tangent of pi over 4. Tangent of pi over 4 is 1. Minus 1/2 times log of secant of pi over 4. Secant of pi over 4? Do you know that one? Square root of 2. So cosine of pi over 4, that's the square root of 2 over 2. But of course, that's the simplified because, we don't like square roots in the denominator form. It's also known as 1 over square root of 2. If you flip it, flipping cosine gives secant, so we get square root of 2. Now, that's when we plug in at pi fourths. When we plug in at 0, well, 0 times tangent of 0, 0. Log of secant of 0, 0. And therefore, that's what you get. So we end up with pi over 8 minus 1/2 log square root of 2, which you can, if you like, write it as minus 1/4 log of 2. And if you're curious what I did at that last step, the log of square root of 2 is log of 2 to the 1/2, but I can pull a power down, so 1/2 log of 2. All right. And there you go. That wasn't so bad. That wasn't bad at all. All right. The power of switching coordinates. Now, could you have done this in another way? You may have. I think if you did integration by parts here and didn't go crazy, it could work. But I feel like this is a little bit simpler, a little simpler process. And that's our goal. We want things to be simple. We want things to work out nicely. So, on to today. Now, we're interested in integration, which is about finding totals. And sort of we have a progression that we've gone through. Or I should say that we're going through. So when we first started doing integration, we looked at our inputs as being intervals. So we integrated over an interval. Usually we think of it as a to b of f of x dx. So this is an I, that's not a 1. So it's just a single back a year ago when we started learning about integration, integral from A to B. It's really an integral over one-dimensional region. Now, we said, hey, we can go to two-dimensional regions. Then we can say, okay, we're integrating over some region, and now it's two-dimensional, so we don't have to integrate a function of one variable. We can integrate a function of two variables, f of x, y. But now, we say dA. Because when we're breaking things up into little bits of area. So it used to be dx, which is sort of measurements of one-dimensional things. We want to measure two-dimensional things, so we talk about dA. So for today, we want to go to our next step, or sort of our logical progression, if you will, which is to say, suppose now I have a solid shape. So here's some sort of strange solid shape, and I'll call it S for solid. And I want to integrate over my solid my function f of x, y, z dv. So because I'm over a three-dimensional region, the thing I integrate can have three inputs. And when I break things up, well, the way I break things up is I break things up into little tiny pieces, which consist of volume. Now, the basic idea never changes. So whether we're doing 1, 2, or 3 or more iterated integrals, we never change our basic underlying idea, which is take what you're trying to find the total of, break things up into small parts, and add the parts back together. And that gives us the results. All right. Now, there is one thing you should hopefully pick up on, which is the number of integral signs that we use corresponds to sort of the dimension of our problem. So when we see a one integral sign being used, that corresponds to a one-dimensional type problem. When we see two integral signs, that's a two-dimensional type problem, and so forth and so on. So we're going to be fairly consistent about that going forward. That might not mean much now, but as we get towards the end of this part of the course, you'll see, okay, that's how I understand what's going on. So here's our basic underlying idea, is we're going to take our solid shape, and we're just going to split it up into little tiny pieces. And because we're in Cartesian coordinates, the way we like to split things up into pieces is we like to look at perturbations of how we identify points. So in Cartesian coordinates, we have x, y, and z. So when we're thinking about perturbations, we're thinking about a little change in x, a little change in y, and a little change in z. And that shape that gets formed when we perturb things is a little tiny box. The size of the box, well, that's just, you measure the sides of the lengths, change in x times change in y times change in z. So we get that the total would be, well, we sum over all the boxes, f of x, y, z, delta v. Now, why are there three sums? Well, because I can be going in three different directions. So I can go in the x direction, in the y direction, and the z direction. So that's why there's three different sums. You really have to index for each direction. Where are you in terms of the x? Where are you in terms of the y? Where are you in terms of the z? Now what happens is that in the limit, as these boxes shrink down to a very small size, these go, say, to size 0, then your approximation gets better and better. And if the limit exists, we say that's the integral, and that's what we denote by this triple integral of our solid. Now, that's sort of the idea. What's the practice? Well, it won't surprise you to discover we're basically going to do the same thing that we were doing before, which is we're going to slice things up and work in slices. So we were doing this when we did our two-dimensional region. We said, okay, instead of breaking things up into little tiny squares, we said, okay, first we're going to break things up into little tiny strips, and then ask what happens in each strip. So here, we're going to do the same thing. I'm going to take this solid, I'm going to take a slice at a particular fixing one of the variables. So for instance, this slice would correspond to fixing a z value. And when I look at this, so this light here, this is z equals some k. And when I look at what's happening to this, I can say, well, look, I know this is z equals fixed. So this is in the plane z equals k, but really that slice exists somewhere. I can think of it as just saying it's like in the xy plane. It's a two-dimensional object. So if I want to understand what's the contribution of that slice, I say, okay, look at this integral here, that total from the slice at z. So whatever this integral does in the xy plane, that's the contribution from that total at that slice. Of course, that's just one slice. I have to add all the slices back together. But how do you find that total? And the answer is, well, that's a two-dimensional region, and so we just do what we did before. We integrate what a two-dimensional region would look like. So any level of integration is going to turn out, we're going to rewrite it in a form of iterated integrals all the time. That's when we actually have to find an integration, that's how we're going to do it, is iterated integration. So that's our idea. Okay. Now, some things to note here. If you look at this, we have 3 layers. And it's important to understand what's happening at each layer. So the outer bounds, they always will go between 2 different numbers. The next layer, the middle bounds, they go between 2 different curves. And the innermost layer, the inner bounds, always go between 2 different surfaces. So once you have that mentality, it helps you to understand what's happening, helps you to visualize these surfaces, and also to set them up and manipulate them. And we want to be able to do that. Now, there's also another thing to think about, which is how do you slice? And what we mean by that, if you go back to our picture here, so here's our picture. We'll use this one, it's the same picture. We said, well, you could slice it where you hold z fixed, and then look in terms of your x, y, what's happening. But that's not your only choice. You could also slice in a different direction. Maybe you slice this way, or where you hold x fixed. Or maybe you slice that way, where you hold your y fixed. All of these are allowed. And so you get many different options. See, when we were doing a two-dimensional region, we only had 2 options, vertical or horizontal. Now we have a full menu of options. 6 different possibilities. And so you get your dx, dy, dz, your dx, dz, dy, and so forth and so on. All of them are perfectly allowed. Now you'll notice I've boxed one. dz, dy, dx. The reason I've boxed that one is not to say it's more correct than the others, but rather to say that this particular order of integration is the one that you're most comfortable with. Because when we've started raising you in your mathematical knowledge, we start by having you think, okay, one direction, and we start calling that x. And then we said, okay, now go up to 2. And you think, okay, y, and y depends on x. And then we said, okay, maybe there's this thing called the third dimension. And we say, think of z, that's depending on x and y. So this is the one that you're most comfortable with because of the way you've been raised. None of them are more or less correct than the others. It always comes down to which one is the easiest to work with, and by default, I would say try this one first. Just because I think this is the one you'll feel most comfortable with. All right. So let's try this out. So find an integral over a solid of x squared yz dv, where s is a pretty simple solid. We have x going from 0 to 2, y going from 0 to 2, z going from 0 to 1. If we were to sketch this solid, what would I see? Yeah, I'd see a box. X goes from 0 to 2, so here's 2. Y goes from 0 to 2, here's 2. Z goes from 0 to 1, there's 1. So when you sketch this out, what you end up with is a box. So that's a fairly straightforward region to work with. Now, we have to make a choice. What's the order of integration we want to do? Because we have 6 different options. Which one do you want? Well, I said dz, dy, dx, so let's start with that. So integral x squared yz dz dy dx. Now we have to set the bounds, and here's the thing to remember, that the bounds link up in the same way. Namely, the innermost integral links up with the innermost d whatever. The middle integral links up with the middle d whatever, and the outer one links up with the outer one. Not very surprising. In fact, it's what you would want to be true. So good news, it's true. Okay, so I like to work from the outside in. So where does x go between 0 to 2? Where does y go between 0 to 2? Where does z go between 0 to 1? All right. Now, to actually do this, we can do one thing. We can, of course, integrate one layer at a time, but we can also do the trick we talked about when we first started integration, which is to say, wait a second, these are essentially three integrals that we can pull apart. Because the reason we can pull them apart is two things. See how the bounds are nice? None of these bounds depend on the other variable. So it's not like I see a function of y or a function of z showing up. These are numbers to numbers. So when you're integrating over what would correspond here to a box, then you can pull it apart if you can pull your function apart. And you can. So in the interest of speeding up our discussion here, because there's a lot of fun stuff coming, I can say, look, this will separate into the integral from 0 to 2 of x squared dx, integral 0 to 2 of y dy, and the integral from 0 to 1 of z dz. The first integral, well, 1/3 x cubed from 0 to 2. The second, 1/2 y squared, 0 to 2. And the last one is 1/2 z squared from 0 to 1. From the first integral, what do we get? 8/3. From the second one, we get 4/2. We can call that 2. From the last one, we can get 1/2, which we can call 1/2. Or, simplifying, we get 8/3. All right. Well, you always got to start with the good warm-up one. Now, this is a case where the order of integration didn't matter. There will be times when the order of integration might matter. So, think about it. Think about it. Don't just always rush in. Say, look, what makes my life easy? Okay. We can, of course, have more interesting bounds. Like I said, we go between numbers on the outermost integral. We go between functions, which are curves, on the middle layer, and we go between surfaces on the last one. So we can have more interesting things. So this one, well, we can't pull it apart. So you got to work it through one layer at a time. So we work it through. So -2 to 5, 0 to 3x, and we start by integrating with respect to z. What's the integral of 4 with respect to z? 4z. And then we're going to evaluate from z equals y to z equals x plus 2, dy dx. Carry out the evaluation. So we'll still have the integrals, -2 to 5, 0 to 3x. We get 4 times x plus 2, which I can write that as 4x plus 8, minus 4 times y, which I can write as minus 4y. And we're going to integrate with respect to y. Well, so we carry that integral out. -2 to 5 of, what's the integral of 4x plus 8 minus 4y with respect to y? The first term? 4xy, because 4x is a constant when we're integrating with respect to y, so it's essentially a constant. Integral of a constant would be a constant times y. Integral of 8? 8y. Integral of minus 4y? 2y squared. Yeah, and it's minus 2y squared. Evaluate that. Y equals 0. to y equals 3x dx. So we need to plug things in. The nice thing is when we plug in 0, we get 0. So we plug in 3x, and we get, well, 4x times 3x. That would be 12x squared. Plus 8 times 3x would be 24x. Minus 2 times 3x squared. Well, that would be minus 18x squared. So integral negative 2 to 5. Before I integrate, I can see that there's things which combine. So all right, this says 24x minus 6x squared. All right, so what's the integral of 24x minus 6x squared? 12x squared minus 2x cubed, right? So you add 1 to the exponent and you divide, and the first term will divide by 2, which is why the 24 becomes 12. The second term will divide by 3, and that's the reason the 6 became 2. And evaluate that from negative 2 to 5. Whoops. Negative 2 to 5. And we'll get 12 times 5 squared, which is 25, minus 2 times 5 cubed, which is 125, minus 12 times 4, which is negative 2 squared, minus 2 times negative 8. And we can stop there. We don't have to keep going. For instance, we don't have to know that this is 300 minus 250 and that we're subtracting 48 plus 16. That's not important to know. Or that this is really 50 minus 64, which would give us negative 14. We don't need to know that. But suppose we did. All right. Should we be worried that we get a negative value out? No, not necessarily. It depends on the context. Right now, these are just abstract totals. Totals can be positive or negative. Now, if we get to a point where we're actually saying that the integral represents something, and we will get to that, we're going to look at applications. That's going to be what happens in our next couple of sessions. It might be a negative answer is bad. So just understand the context. Negatives don't always mean that it's wrong. Okay. So, what's our big challenge going to be? The actual integrations aren't so bad. You just do it one layer at a time, and you be patient. Nothing happens. But the challenge is going to become setting up the bounds, and the even bigger challenge is how do you change the order of integration. So we want to talk about that process. All right, so how do you change the order of integration? Which really comes to saying, how do you set the bounds up? Well, what do you need to do? So the first thing you do is you identify the bounds. Now, the bounds can come in two different ways. You may have an integral already given to you, in which case you say, okay, take that integral and read off what the bounds are telling you. Or you may just have, like, here are some surfaces which bound a region. So there's different ways they might deliver to you. Okay, step 2, draw a picture of the solid you're working with, if you can. It helps tremendously. Now you might think, what if I'm not very good at drawing and it's on an exam? We give you pictures on the exams because this is not a drawing class. We figure it's already challenging enough without having to draw things. So don't panic if you're worried that you're going to have to draw something complicated. The times when we don't give you a picture, what you have to work with is a fairly simple object. Now, there's a note that says, look, if you don't know what it looks like, work one dimension at a time. Say, okay, what's happening in one direction? Maybe it's the x, or maybe it's the y, maybe it's the z. Okay, now add in another direction. So now you're up to 2 dimensions, and then add in a third. We'll go through some examples about what this means. Well, once you have that, you start labeling things. So you label the bounding surfaces as needed. Now, you might say, what do you mean as needed? Well, maybe I'm integrating my innermost integral layer is with respect to z. Well, that means that I need to go from z equals some surface to z equals some other surface. So that says solve for z in those surfaces. Because remember, the innermost integral always goes between surfaces. So you have to say, okay, what's your innermost variable? That's what you need to solve for. So that's what we mean by solve for appropriate variable. And now work from the outside in to determine your new bounds. And I'm even going to include this. I like to say this as my pro tip. To help simplify the process, look down an axis to reduce the dimension. Because when you're starting, your outer integral is just between two numbers. You don't have to see the whole shape to figure out what those two numbers are. So simplify it down to something easier to work with. You can look down an axis and it simplifies your three-dimensional shape. All of a sudden you're seeing its sort of, if you will, two-dimensional shadow. And that can help you simplify what's going on. You can then even simplify that if you need to. But oftentimes once we get down to 2 dimensions, we feel more comfortable. And again, I think that the process will become more clear as we do some examples. And we will do many, many examples, like 2, maybe 3 if we're lucky. Well, these take time. Okay, so let's begin. So here's an example problem. So we want to change the order of integration. We have this integral, 0 to 4, 0 to 2 minus a half z, 0 to 1 minus a half y minus a fourth z, f of x, y, z, dx, dy, dz. We want to go to dz, dy, dx. So we definitely can't integrate this because we don't know what f is. This is all about the bounds. All right. Well, let's start by understanding what's going on. So what does this outer integral tell us? Z goes from 0 to 4. So the outer integral tells us z goes from 0 up to 4. What does the next layer tell us? So it's about y, and 0, 2. So 0 less than or equal to y, less than or equal to 2, minus a half z. What does the inner integral tell us? It's an x integral. It goes from 0 to that other surface. 0 less than or equal to x, less than or equal to 1, minus a half y, minus a fourth z. Now, suppose we wanted to draw this. Well, because we want to draw it. So this is essentially step 1. We've identified the bounds. There they are. Step 2 says draw a picture of the solid. And this says work up 1 dimension at a time. So let's just start in the first case. We start with z. So z, here's z. I like to think about it straight up and down. Where does z go from? 0 to 4. So 0 to 4. Woohoo! Okay, that's easy. All right. Now we add a dimension. Okay, so next layer. Okay. So I have z, and now I have y. So I know z goes from 0 to 4. That's what this tells me. Well, y goes from y equals 0, which is this line, to y equals 2 minus a half z. So if I sketch y equals 2 minus a half z, I can start by thinking, okay, it's a line. Y equals 2 minus a half z is the line. I can see that. And so oftentimes if I have a line, I just need to know 2 points and I can connect. So let's pick 2 convenient points. Let's pick the point at z equals 4 and at z equals 0. If I plug in z equals 4, what do we get? We get 0, which means that one point on the line is actually right there. If we plug in z equals 0, what do we get? 2, which means that the other point will be 2. So that tells us that we're doing this part right here. So if we were to successfully navigate our first integral, our what's left, our last 2 layers, would be over this shape. It's a triangle in the YZ plane. Okay, well, what's the last thing? Well, we need to get x. Okay, so we know we have here's a 4, here's a 2. I'm going to sort of do some little pointillism here. So this is our shape. All right. And now we're adding our third direction. So we have y, we have z, and we have x. So we're going from x equals 0. What does x equals 0 correspond to? Well, x equals 0, if we were on the line, it's a point. If we're in the plane, it would be the y-axis. If we're in three-dimensional space, x equals 0 corresponds to what? It's the yz plane. Okay? So x equals 0 is this whole plane right there. Well, that's nice. How about this one? X equals 1 minus a half y minus a fourth z, because that's where the other surface is. Now, we can rewrite this. This is the same as x plus a half y plus a fourth z equals 1. Yes? It's true. True. True statement. True statement. Okay. What kind of surface is that? It's a plane. All right. How do you sketch planes? Well, you probably think, well, the way that you normally sketch planes, Steve, is you just sort of draw a little square and say, that's the plane. But when we're drawing bounds, we kind of got to be a little bit more precise. But here's a nice way to figure out what a plane does. Is a plane is determined by 3 points. So if you know where 3 points are, you know where that plane is. So let's pick 3 convenient points. And here's the 3 convenient points to pick. Where does it hit the axes? Now, how do you figure that out? Well, the answer is, suppose I'm on the z-axis. What's true about x and y? They're 0, which means you just sort of cover it up. Say, if I'm on the z-axis, I need to have 1/4 times z equals 1. So what does z need to equal? 4. So the plane is going to be involved at that point. Okay, suppose I'm on the y-axis. Well, what needs to be true? Y has to be 2. Oh, which means the plane is going to hit this point. And suppose now I'm on the x-axis. What's true about x? 1. So, our plane, when it hits those 3, it's the plane that's going to contain those 3 points. Now, of course, it extends, but that's what it's going to consist of. Now, what's our shape? Well, what is x doing? It's starting on the back side, and it's going to come forward until it hits the plane. Okay? So, what's our shape? Our shape, it's a tetrahedron. In other words, it's sort of a 4-sided object. And so I'm going to clean it up a little bit here. So we go 1, 2, 4. So here's our shape. There's the 4 sides. Okay? There's the YZ plane in the back, the XY plane on the bottom. There's the XZ plane here, and then there's this Mr. Slanty. Okay. All right? So do you see our shape now? Do you see what it looks like? Okay. We've successfully done step 2. That's the I won't say that's the hard one, but it's a harder part. Okay. All right. I better make sure we leave enough space to write down the answer here. So we're going to put a box here and say, and this is the answer. Integral, 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 and then it's still the f of x, y, z. And now dz, dy, dx. Okay. So if we were to go through and label our various surfaces here, so this back surface, this corresponds to x equals 0. This bottom surface, that corresponds to z equals 0. This side surface here, that corresponds to y equals 0. And then Mr. Slanty, that's this plane. X plus, now that's not a technical name. You don't have to call him Mr. Slanty. But, okay. So those are my surfaces. So I've identified what my surfaces are. they're all labeled. And I should say I should probably solve for the appropriate variable. So let's think about what the appropriate variable is. The inner layer goes between surfaces. So I want to solve for my surface in terms of which variable? Z. Okay, so if we solve this for z, that's 1/4 z equals 1 minus x minus a half y, or z equals 4 minus 4x minus 2y. Okay, so we're now ready for our last step, which is to actually start working on the bounds. And we're going to start on the outer bounds, which are x bounds, then we'll go to y bounds, and then we'll go to z bounds. So how do we start? Well, here's the thing is, the last thing I'm going to worry about is the z. So because it's the last thing I'm going to worry about, what I'm going to do is I'm going to imagine that I had my eye up here, and I were looking straight down. So I'm looking straight down the z-axis. You have to imagine that's an eyeball. That's kind of a weird-looking eyeball. But okay, so imagine that you're looking straight down the z-axis, because that's the z-axis is the last thing we're going to say. So what I like to do is I like to visualize I'm grabbing a hold of that z-axis, and I'm just going to turn it so that I'm going to be looking straight down. If I look straight down, what will I see? The answer is I'm not going to see the z-axis anymore. It's going to be just that point. That's the z-axis, because it's all going to be looking straight down it. So what I'm going to see is I'm going to see a picture here in the xy plane. Well, when I look at the picture in the xy plane, what shape am I seeing? A triangle. Where does x go from? 0 to 1. Okay. And then y, well, on the boundary it goes, of course, 0 to 2. But we have this. There's our triangle. That's what we're seeing when we look down the axis. So now we're ready to start talking about the x. So start with our triangle. Where does x go from? 0 to 1. We've already mentioned that. Okay. Now, I'm holding x fixed, and I ask the question, what happens to y? Well, where does y go from? I start here. What's this curve? Y equals 0. And I go up to this curve. Now, we need to figure out what this curve is. Well, it's not so bad. It's a straight line. Do we know what the y-intercept is? 2. Do we know what the slope is? Negative 2. So this is the y line, y equals 2 minus 2x. So 2 minus 2x. Now, so that tells me what's happening in my my xy plane. For the last one, I come back to the picture and I say, okay, what's happening? Well, here I'm going to go from the bottom is going to be right there. Okay, that's my xy plane. And then I'm going to go up. So I start there, and I go up till I hit what? Well, I go until I hit my slanted face. So my bottom bound, that's the xy plane, that's z equals 0. So I'm going from 0 to my top, which is my surface, 4 minus 4x minus 2y. All right. And that's it. That's the problem. We're done. And now you're thinking, cool, I get to do 7 of these on the next exam. No, only maybe 1 or 2 or 3. Probably there's even more fun stuff coming. So this is not the funnest stuff. All right, any questions about the process? Okay then, let's do another one. So this comes from an old final exam. Well, it's sort of a simplified problem from an old final exam. Let D be the solid with x, y, z greater than or equal to 0. Y is less than or equal to 1. So here's y equals 1. So that's one thing. X plus z is less than or equal to 1. Now x plus z equals 1. In terms of the picture, what does x plus z equal 1 look like if I'm in three-dimensional space? X plus z equals 1 is what? Well, if you just saw x plus z equals 1, you would probably think to yourself, oh, that looks like a line in the xz plane, right? You know, because it just involves x and z. It would be this line in the xz plane. But if I said it was in a three-dimensional space, well, what happens is because there's no y, you're just moving that line backwards and forth, back and forth. So you end up causing a plane. And the plane you cause is this plane right here. That's x plus z equals 1. All right. There's a couple of other things that we can point out. This bottom part, that's the xy plane we're sitting on. What does that correspond to? Yeah, z equals 0. There's this other side over here, which is part of the xz plane, which is y equals 0. And then, of course, there's this z less than or equal to 1 minus y squared. Well, if you just saw that, z is less than or equal to 1 minus y squared, you'd think, okay, that's in the yz plane. That would look like a parabola. In fact, it's this part of the parabola right here. But then, you say, well, what does it look like in 3 dimensions? You just copy it back and forth. So what you get is you get this sort of like skateboard ramp shape thing going on. There's a bit of a slope to it. That's your z equals 1 minus y squared. And of course, there is another backside here, which is this side here, which is the yz plane. That's x equals 0. Okay, so there's our shape. See, now this one is slightly different. They didn't give us an integral. They said, here's the shape. And what we want to do is we want to do the integral. So we're going to carry out this integral, or, well, we're going to think about carrying it out. Okay, so let's at least get the bounds set up. All right, so let's think about the bounds. Now, really, if it just says find the integral, we can set our bounds in any way. But there's a hint, and you know what? I'm going to go on the faith that the people who wrote this problem, they care about us. And so they wouldn't give us a hint that was bad. So we're going to go with their hint. And then say, okay, so our dv is dx, dz, dy. All right, so a slightly different order. So if we were to start the process to label things, what's the last thing we're going to label? Well, the last thing we'll label is the x, because we work from the outside in, which means we should be looking down which axis? We should look down the x-axis. So we look down the x-axis. As we look down the x-axis, what will we see? Well, we're going to see y and z. The x-axis is just that point. And what we'll see is we'll see this curve. Z equals 1 minus y squared. And we're going from 0 to 1. So now we can start labeling things. Where does y go from? 0 to 1. All right. Where does z go from? 0 to 1 minus y squared. Now, where does x go from? Well, when we think about what x does, we should think about x is going to move parallel to the x-axis. So in terms of our shape, we're going to start at the back, and we're going to move parallel to the x-axis until we hit the front. So what's the back shape? X equals 0. What's the front shape? Well, the front shape is this plane, x plus z equals 1. We have to write in terms of x, so this becomes x equals 1 minus z. So we go 0 to 1 minus z. All right, and now we're set up. We got to go ahead and finish the problem. So, let's just work it out. We got to get practice on doing these integrals. 0 to 1, 0 to 1 minus y squared. And now we're integrating 30, well, with respect to x. That's not so bad. That's 30x. Evaluated, x equals 0 to x equals 1 minus z. And then we're going to do that dz dy. So integral 0 to 1, integral 0, 1 minus y squared, and that'll be, well, it'll be 30 times 1 minus z. So I can write that as 30 minus 30z, right? And then plug in 0, you get 0. So there we go. There's our next layer. One layer down, one to go. Well, actually, two to go. Okay, so what's the next one? Well, 0 to 1. I can see as I'm going down the page, I'm getting more nervous, and I'm starting to write it a little bit smaller. Well, yeah, of course, we need more space. When you integrate the next layer, it's with respect to z. So that will become 30z, and then here, minus 15z squared. And then we're going to evaluate from z equals 0 to z equals the quantity 1 minus y squared dy. Now, well, what is that? Now, I'm going to make a little note to the side here, which I think is going to help me. 1 minus y quantity squared is the same as, this is totally true, you can check it out, y minus 1 quantity squared. And so, I can replace 1 minus y by y minus 1. And the square does that for me. So if we do this, we'll get 0 to 1. So 30 times y minus 1 squared minus 15 times y minus 1 squared squared, which is y minus 1 to the 4th. Now we could, of course, multiply this out, but we love ourselves too much. We don't want to put ourselves through that, well, so we're not going to. Instead, we're just going to work this out. So here, you could do a couple things. You could think of it as a u substitution, or you just say, okay, well, what does it become? So if I add 1 to the power, because, it's y minus 1. Okay, so this will become y minus 1 cubed, and then I divide by 3, so that's at 10. Then here, minus, so I'd add 1, so that'd be y minus 1 to the 5th, divide by 5, so there's a 3. All right, and we can do this because y minus 1 is essentially y, it's a shift. And if you don't like this, you could also do this by doing a u substitution of u equals y minus 1, but you don't need to. So, we're almost there. We plug in y equals 1. Well, if you plug in y equals 1, 1 minus 1 is 0. So, we're going to get 0 minus 0. Okay, well, that's not so bad. Subtract, plug in 0. 0 minus 1, that's negative 1. If I cube that, I'll get negative 1. So it's negative 10. Here, I'll get negative 1 to the 5th. It's negative 1. That's a plus 3. And if you simplify that, because of this negative here, it's really like 10 minus 3, also known as 7. And there you go. There's the answer. Now, I mentioned that this was on an exam. What I didn't mention is that this was problem number 7 on the exam. So problem 7, the answer was 7. Good times. Good times. These exam problems, they're a lot of fun. All right, let's do some more problems. So, rewrite the order of integration. So we have the integral negative 2 to 2, the integral 0 to 4 minus x squared, and the integral from 0 to 4 minus x, f of x, y, z, dy, dz, dx, and we're changing it to dx, dy, dz, but then we stop, because we can't integrate it, because we don't know what f is. So we start saying, okay, so the process, we need to figure out our current region. So we start by reading off the bound. So we start from the outside, work our way in. We know that x goes from negative 2 up to positive 2. So that says if I were sketching x, well, let's just sketch x. Here's x. So I'm going from negative 2 to positive 2. Okay, so that's x. Cool. Now our next layer, y. Well, what does y do? We're going to go from the lower bound of 0 to our upper bound of 4 minus x squared. Okay. Well, what does that do? Well, here we're now in the xy plane. We know we're going from -2 to +2, so we're going from 0, which is this line, y equals 0, to y equals 4 minus x squared. Well, 4 minus x squared, that's an upside down parabola. And it happens to intersect at +2 and -2. And so it looks like that. And here this intercept is at 4. So the region in the xy plane is that region there. Now that leaves us with one more to set up. Okay, 0 to 4 minus z. So what is that? Oh, whoops. I wasn't paying attention. The middle layer is not y. The middle layer is z. Pay attention, pay attention. dx, dz. So this is z. This is in the xz plane. Good. Whew. Almost had a catastrophe there. So let's see. So the last layer is the y. Now I knew something was wrong because I said, oh, there's a z there. Oh, yep. So y, we go from 0 up to 4 minus z. Now, to get this picture right, let's think about what's happening. So let's start by translation. We know we have our three axes, x, y, z. X is going from -2 to +2. So that's, back here is -2, up here is +2. And then we have this plane, xz. So there's this shape here, this upside down parabola. So this right here, I'm going to shade it because I notice that I have this y equals 0, which corresponds to the xz plane. So this is essentially the back side. Now what happens is I'm going from the backside 0 out to 4 minus z. Now that is in particular y equals 4 minus z. Now if we think about what that looks like, that's a plane where if we start by looking in the yz cross section, it starts at 4, which is actually up here, and then it goes down. Okay? So again, this is a plane. So it's going to always look like that shape there. Okay? So it's this plane slanted down. Now, to finish off what this shape is doing, well, we always go out till we hit the plane. So down at the bottom, we don't go very far. But if we move up, we'll see we go less far. In fact, in particular, from any point, we go until we hit the face of the plane. So what does the shape look like? Well, it looks vaguely like the following. It's like a doorstop kind of shape here. So that we have this surface here, I'll mark that here in green. That is our surface, y equals 4 minus z. Okay, so there we go. There's our shape. Boom. Okay? All right, so now we have our shape. Well, that's pretty good. That helps a lot. So we can start moving towards setting up our new bounds. So number, curves, surfaces, f of x, y, z. And this is our order, dx, dy, dz. Now, the last thing we're going to set is x. So, if we're going to have x be our last thing to set, we're going to start by looking down here in the x-axis. So if we look in the x-axis, what do we see? Well, the answer is we're going to be seeing this YZ plane. Okay? The x-axis is this point at the origin. So there's our x-axis, but we're looking straight down into it. So we're looking straight down, so we can't even see it. There we go, straight down. Wow. All right. Now, what do you see if you look in that direction? And the answer is that we see this y equals 4 minus z. That's the shape. So we're seeing a triangle coming along here. Now we're ready to start figuring out our bounds. Where are the intercepts? Well, we start up here at 4, and we also intercept down here at 4. So where does z go between? Well, it goes from 0 to 4. That wasn't so bad. Now let's go to our next layer. In our next layer, we say, okay, where does y go from? So what I'm thinking is I've hit a z value, and I'm looking, where does y go between? Okay? So I'm going to go from this line, well, that is 0, out to this line. Now, what do I need? Well, I need to have it of the form y equals, because these are y bounds. Oh, it's already in the form y equals. That's very nice. So 4 minus z. All right, and now that's it. That's our next layer. Now we come to what? Well, we come back to this picture here. Okay, so the question is, what's our last thing? Well, let me redraw this picture, or at least attempt to redraw it. We'll try to do our best. So we have this back face here, and then it's coming out, something like so, and we have this. Okay, there we go. Now this face right there, this, which was the one in green, that is this line segment here. That's just seen from the side. Now what are we after? Well, we're picking a point here in YZ, and we want to say what happens. Where do you go between? In particular, what we want to think of is, where does our x go between? Well, our x is going to go from the two sides. Now, what are these surfaces? Well, the surface here is this sort of curved surface. So you have two of them. You have one in the front, and then you have a different one showing up. It's harder to see the one in the back, it's because of our angle, but you have this other surface here in the back. So where did those surfaces come from? Well, these are coming from the 4 minus x squared. So in particular, what we're seeing here is that they're coming from the z equals 4 minus x squared. But remember, we have to solve for x. So x squared would be equal to 4 minus z, and so we get x is equal to the square root 4 minus z, or x equals minus the square root of 4 minus z. And the question is, well, which one do we need? And the answer is, you need both. The front one, that's the x equals plus the square root of 4 minus z. And then this back one, that's x equals minus the square root of 4 minus z. And where do we go? Well, we go from the back to the front. Small x to large x. So minus square root 4 minus z to plus square root 4 minus z. And now we're done. We've set up our bounds. So the harder part in this problem is, getting the picture. Once you have the picture, it's not too hard to explore. Oftentimes we'll provide the picture, but again, you can build it up one layer at a time. Okay, what happens in x? Now add in the next variable, z. Now add in the x, y, and z. Trying to understand. And once you understand, well, life is good. Okay. I think we have one more problem. And let's do it. Let's get it done. Woo! So, let S be the solid bounded by z equals 0, y equals 0, y equals x, and z equals 2 minus 1/2 x squared. And write the integral as an iterated integral. So we got to start by sort of understanding what happens here. So let's think of our shape here. Okay, so we're going to start in 3 dimensions. We really have, what is this, 1, 2, 3, 4 surfaces. So we should talk about all of these. Now z equals 0. Z equals 0, that's pretty good. That's down here. That's the z equals 0 is the xy plane. So we have a floor. Okay. Well, how about y equals 0? Well, y equals 0, that's this part. So this is y equals 0, and it's the xz plane. All right, 2 for 2. Nothing too tricky here. Now, let's try another one. Y equals x. Now, if I think about y equals x, what that corresponds to is in the xy plane, it would correspond to the line y equals x, that line that comes out at 45 degrees. When there's in 3 dimensions, it corresponds to a plane. So it's this plane. It's actually a lot like this plane here, but you just sort of swung it a little bit. So you swung it around 45 degrees. Okay, so this is the plane y equals x. All right, well, so we got those 3. That's not so bad. And now our last piece. Well, our last piece, let's put it down here. That one we might have to think a little bit more about. So you have x, y, z. So we're told z equals 2 minus 1/2 x squared. Now that one actually isn't so bad if we think about it just in the xz plane. In the xz plane, it's an upside down parabola. So you come up to 2. So this is z equals 2. And now you go down. So you're going to open down this way. And you would also open down that way. All right. Where do you hit? Well, where do we hit down here? The answer is, well, that would be where z equals 0. And if I want z equals 0, I need 2 minus 1/2 x squared to equal 0, which would happen here at 2. All right. Well, what's this shape? Well, once you have this, you just copy it back and forth. So that's our shape. All right. So there we go. Those are our bounding surfaces. Now, someone pointed this out to me a year ago, and I believe I really need to add plus. We're going to say it's in the positive orthant. So x, y, z are all greater than or equal to 0. All right. So here comes the tricky part. So if we start building this up, so let's assume x, y, z is all greater than or equal to 0. Well, you have the floor, you have this sidewall, then you have this thing coming out at 45 degrees. So that's great. So let's see if we can't find a good way to fit this all in. All right. Well, looking here, we want to be contained by both the xz plane, and then we have this other part here. So I'm going to sketch this other part. So this is our curve. Z equals 2 minus 1/2 x squared. And now we can say, okay, we're going to start here. We have our floor, is always going to be there. And now we're going to move forward. But where do our curves intersect? We can actually mark them all. There's going to be an intersection between these two. They intersect on the x-axis. Between these two, they intersect on the line y equals x. Between these two, they intersect here. say between these two, where do these two intersect? Well, they intersect on this stretch right there. If we do, where do these two intersect? The answer is they intersect here. And how about where do these two intersect? And the answer is they intersect there. So if you look at where the surfaces intersect, that tells you what's going on. So our shape is the following. And this is the one that's harder to see, but okay. So what we have is we have four pieces. So this face, the curved face, that's our z equals 2 minus a half x squared. The other faces are easier to spot. So downstairs, this face down here, that is the one where we have z equals 0. The back face, well, which one is that? Say back on this side, that is the one where we have y equals 0. And our last one that we haven't marked yet, this face over here, that's the one where y equals x. Okay, so that's our shape. That's our shape. Another wedge shape. Well, wedges are common, especially when you have very few planes coming together. So that's not so bad that it's another wedge shape. Okay, so you might say, okay, we did this rather quickly here. So I think it's worth taking a second and explaining, what was happening here. Well, the big step that allowed us to make a lot of progress in what seemed like a very short time was to say, where do things intersect with each other? And so that's how we added in all these extra lines here. And so again, you just pick any two surfaces. Say you pick these two surfaces. So what's this? Well, if I ask the question, when does this plane hit this surface? Well, it's along this sort of arched line here, roughly about there. So that's where they intersect. And so finding when the surfaces intersect, that gives you the edges. And once you have the edges, that outlines the shape, and then we have our picture. Okay, well from here, we can start to sort of understand what's going on. Now, if we wanted to help us get a full picture, the other thing to do is to look down our axes. So we have three different axes. So we have our x, y, and z. So let's look down the x-axis. So if we look down the x-axis, well, what do we see? Okay. If we look down the x-axis, the picture that we're going to see is we're going to... All right. I picked the hard one first. That's why I'm humming and hawing. Let's come back to the x-axis. Let's look down the z-axis, because if you look down the z-axis, you can see the shape. It's right here. So, on the z-axis, when we look down, what do we see? Well, we see this triangle. Now, where does it hit? Well, it comes out here to x equals 2. And now, what's this line? This is the line y equals x. And so, our shape is this region. Okay, so there we go. That's our shape. Now, suppose we look down the y-axis. Okay, so if we look down the y-axis, what we're going to see is xz. And what we see is we see this shape here. Okay, what is that? Well, it's this curve, z equals 2 minus 1/2 x squared. It hits up here at positive 2. It also hits downstairs at positive 2. And we get our shape. So now All right, back to the one I was humming and hawing about, the x-axis. Well, why is the x-axis so hard? The reason the x-axis is a little bit harder to see is we're not up against the yz plane. See, in the other two cases, we were really up against the yz plane, so it's easy to read off. But here, we're not. So what are we going to do? Well, that's okay. So we're in the y and z. And now what you can see here is we have this surface z equals 2 minus a half x squared. It's still z equals 2 minus a half x squared along this line. But notice on this line, we're on the line y equals x. So 2 minus 1 half x squared becomes 2 minus 1 half y squared. So I can write, it's actually the same idea. We see z equals 2 minus 1 half y squared. 2 and 2. So we're taking advantage of the fact that we can see that we're in the intersection of the plane y equals x and this surface z equals 2 minus a half x squared. So let's start working through. And we'll fill these in. We can do a couple of them. So let's pick some orders. So integral, 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 f of x, y, z. And we can do any order we want. Suppose we do dz, dy, dx. We said that was the one that was fairly natural. So let's look down the z-axis. Here we go. Now we say, well, where does x go between? Well, the answer is x goes 0 to 2. 0 to 2. Where does y go from? Well, so that would be if we were slicing this way. So it would be from y equals 0 to y equals x. 0 to x. Now, where does z go from? Well, we have to think. If we run up and down, so we're running parallel to the z-axis, we'll start at the bottom, and then we're going to go up until we hit this upper surface. So we're at this surface, z equals 0, that's our bottom surface, and then the top is that curved surface, z equals 2 minus 1 half x squared. 2 minus 1 half x squared. Okay, so that's one order. Now, suppose we did a different order. Okay, integral, 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 f of x, y, z, dz, dx, dy. Now this one's going to feel really similar. Well, what happens is we look down the z-axis, we see the xy plane. We say, all right, where does y go from? Well, we go from y equals 0 up until the largest value would be up here, which is at 2. 0 to 2. Now, we say, okay, fix a y value. Where does x go from? Well, now we're doing a different slice. We're slicing this way. And we're going from x equals y, because remember, I have to talk at x equals y, all the way out to this line, which is at x equals 2. So, y to 2. Now, how about this last layer? The answer is, it's the same thing. We're still running up and down. So this last layer is the same expression, 0, 2 minus 1 half x squared. All right, well, let's do another one. Okay, integral, integral, integral. F of x, y, z. Well, let's see, how about we do dy, dz, dx. So, look down the y-axis. There we go. There we go. There's the y-axis. Now, so here's our starting point. Where does x go from? Well, x goes from 0 to 2. So 0 up to 2. Where does z go from? Well, we think about, we have x, so z is going to go up and down. So we're going to go from z equals 0 to z equals 2 minus 1 half x squared, because that's this curve. 0 to 2 minus 1/2 x squared. Now, where are we at? Well, we're going to now run parallel to y. So we're moving in the y direction. It says we're going to start somewhere back here, and we're going to move until we hit this front. So, where do we start? Well, we start on this face, which is the y equals 0 plane. So we want to write that in terms of y. Well, that's y equals 0. And we move until we hit this slanted face, this face here, which is y equals x. So y equals x. And now we're done. Cool. All right. Well, let's try another one. Integral f of x, y, z. And now let's do dy, dx, dz. Well, so again, we're looking down the y-axis, so we're still looking at this shape. Now we say, well, where does z go from? Well, z goes from 0 to 2. So that's still the same. Now we say, okay, we fixed the value of z. So now we're going that way. Well, we go from here, we're going from x equals 0, so that's x equals 0, to this line. Well, what is that? We need to solve for x. So if you multiply by 2, rearrange, and are patient, now that's a big ask, you'll get x squared equals 4 minus 2 times z. So it says x equals the square root of 4 minus 2 times z. All right? So we're going from x equals 0 to x equals the square root of 4 minus 2z. Now, the innermost layer, it's again this same left-right motion. So we're still going from y equals 0 to y equals x. 0 to x. All right. Well, 4 down. Might as well get a full set. Okay, our next one. Well, let's see, we've done dz, dy. Let's do 0 to 2. Ah! I started filling in. I don't know if it is. Hopefully it is, otherwise I'm going to feel embarrassed. Yeah, I'm in that 0 to 2 mindset. Hope it's still true. Okay, dx, dx, let's do dz, and then we'll do dy. So I'm looking down the x-axis. So that says I'm in the yz plane. Now, where does y go from? Oh, thank goodness, it's still going from 0 to 2. So those bounds were correct. Now, I hold the value of y fixed, and I ask the question, well, where does z go from? Well, I go from z equals 0 up to this curve. So I go to 0 up to 2 minus 1/2 y squared. All right, now the inner layer. Well, for the inner layer, what's happening is we're moving parallel to x, okay? So see how it's the dx? That means you're moving in the x direction. So that says we're going to come from the front face and go till we hit our back face. So that's our direction. So what are the two faces that we hit? Well, one face is this face, x equals y. That's our back, our low value. So we're going to start at x equals y, and then we're going to move forward until we hit this face. Now, right now it says z equals, so we got to rearrange it and write it as x equals. Now the good news is we actually did the work over here. So this is the surface, x equals the square root of 4 minus 2 times z. So y, x equals y to x equals the square root of 4 minus 2z. All right, and for our very last one, our conclusion, what could we be? Well, we know where we're going. Integral f of x, y, z, and then it's dx, dy, dz. So again, we're looking down the x-axis. Now where does z go from? It goes from 0 to 2. So 0 to 2. We slice this way. And we say, okay, well, where does y go from? Well, I go from y equals 0 out until I hit this surface. Well, that's not a surface, it's a curve. Again, I can do the same thing I did here. This is this surface y equals square root of 4. And I said that again. It's not a surface here, it's just a curve. This is y equals the square root of 4 minus 2z. Now, we come here, and what happens? Well, it's the same as in the previous step. We're going from x equals this back face, x equals y, out to this front face, which is x equals the square root of 4 minus 2z. So 0, not 0, y out to square root 4 minus 2z. And there you go. Now, which one is the right answer? And they're all right. Do you need all of them? No, we could have stopped back here, and you're probably thinking, whoa, could have told me that 10 minutes ago. I could have saved 10 minutes of my time to do something else. But, all right, there you go. And these are challenging, but there's a methodical way to think about them. Where are your bounding surfaces? Okay, figure that out. Where do the surfaces intersect? That helps you figure out which pieces you care about. Because once you understand where the surfaces intersect, everything else comes together pretty quick. Look down your axes. That'll help you build up and understand, how do we go in between. When your last integral, say, is dy, that means you're moving parallel to the y-axis. So you're moving in this sort of left-right. When your innermost integral, that's your dz, means your last thing you set up is an up-down integral. And when the last thing is dx, well, it's sort of a front-back. And so once you get the hang of this and you do this for a while, it's not so bad. But you got to put in the time. You got to do the work. And of course, if you do the work, you're going to get better. That's it for now. See you next time.